Hi there, this is Richard Walker from Lucidate, and in this video we're going to look at a vital area of AI and large language models, that of code generation. You've no doubt seen that LLMs can do a pretty good job out of the box in code generation. This is in part due to the presence of websites like Stack Overflow. LLM training corpora accessing these types of communities have a huge amount of coding examples to draw from. Furthermore, there are many fine-tuned models for code generation available from HuggingFace and Ollama, and you can fine-tune your own model, focused on your own specific use cases. Lots of choice. How do you know which is best? One solution, and indeed a very good one, is to check out Hugging Face's leaderboards. This enables side-by-side evaluation of different models producing code in different languages: Python, Java, C++, JavaScript, etc. They show how benchmarks are constructed and allow you to look at the score, the throughput, and memory consumed per model on each benchmark. But some models can perform well on benchmarks and then less well on your own use cases. Indeed, some models are developed simply to beat the benchmarks. So, while these league tables are useful, it's a good idea to consider supplementing them with your own customized tests. In this video, we'll look at both the background to evaluating how good LLMs are at coding, as well as how to construct your own benchmarks that are tailored precisely to how you expect to use your model. As you can see from this analysis, the pros and cons of using standardized league tables and your own benchmarks kind of supplement one another. Each shines out where the other method might not shine as brightly. Hugging Face's leaderboards offer us a convenient, community-validated and broad comparison landscape, akin to a well-trodden hiking trail through a national forest, offering safety and clarity and access to the best vistas. However, this trail doesn't always reveal the unique flora and fauna hidden just off the beaten track, those specialized tasks and nuances specific to our journey. Enter custom benchmarks, the machete in our exploration toolkit. They allow us to carve out a path that's uniquely ours, offering customization, control, and insightful analysis tailored to our specific environment. Yet, this exploration is not without its challenges, requiring resources, expertise, and time, much like preparing for a trek into uncharted territory. So, how might we construct our own benchmarks? Recall in our previous videos where we were comparing different LLMs for language tasks like summarization, generation, and translation. In those videos, we made use of Blur, Rouge, and semantic similarity. Blur and Rouge use the concept of n-grams, matching longer and longer sequences of matched words in our golden source text compared with our machine-generated candidate. Semantic search used the semantic similarity in word embeddings to see how close in meanings the words were, even though the words themselves might be very different. This technique uses the high-dimensional word embeddings to determine the closeness in meaning of words. For a refresher on Blur, Rouge, and semantic similarity, please see the previous video. There's a link in the description and a card on the top of the screen. So, while these measures are useful for evaluating LLMs for natural language processing tasks such as translation, summarization, and text generation, they fall somewhat short when evaluating code. This has motivated other metrics for code LLMs, most notably CodeBleu. So, while Blur has been instrumental in advancing machine translation research, its effectiveness doesn't directly transfer to code synthesis evaluation. This is because code and natural language have some fundamental differences. First, programming languages have a limited set of keywords such as if, for, and while that carry special meaning. In contrast, natural languages have a vast vocabulary. Blur treats all words equally, but keywords in code are more important for correctness and should be given higher weight. Second, code follows a strict hierarchical structure defined by abstract syntax trees or ASTs. This tree-like structure is essential for a program to be valid. Natural language, on the other hand, is more flexible and is processed sequentially. Blur's n-gram matching doesn't capture the structural properties of code. Third, code is designed to be unambiguous and completely deterministic. Each instruction has a precise meaning. Natural language, however, is often ambiguous and context dependent. This makes it possible to evaluate the semantics of code more objectively than that of natural language. Given these differences, relying solely on Blur or Rouge for code synthesis evaluation is problematic. Blur only considers token level matching and ignores the importance of keywords, syntactic accuracy, and semantic correctness. Using Blur might lead to generated code receiving high scores despite having incorrect structure or logic. It could also underrate code that is functionally identical but differs in the surface form from the reference golden source. This is where CodeBleu comes in. By incorporating syntax and semantics, CodeBleu aims to provide a more comprehensive and reliable evaluation of code synthesis results. We'll explore how it achieves this in the next section. So, what exactly is CodeBleu and how does it work? In this section, we'll break down the key components of this particular metric. At a high level, CodeBleu combines 4 weighted components: the standard Blur score, a weighted n-gram match, a syntactic match based on abstract syntax trees, and a semantic match based on data flow. Firstly, we simply look at the Blur score based on n-grams. While this is unsophisticated, it can at least provide some level of similarity between the candidate code produced by the LLM and the golden source. Secondly, and more importantly, we look at weighted n-grams, which take into account the matches between the keywords of that specific language. Thirdly, and more importantly still, there's the syntactic match. Unlike natural language, code has a rigid structure that must follow certain rules. CodeBleu leverages this by comparing the abstract syntax trees of the generated and the reference code. ASTs capture the essential structure of the code while ignoring surface details like the variable names. Finally, the semantic match. The meaning of code depends heavily on how data flows between variables. CodeBleu represents this using data flow graphs where nodes are variables and edges show the dependencies between them. By comparing these graphs, CodeBleu can access the functional similarity of 2 code snippets. Finally, CodeBleu calculates a weighted sum of these 4 components. The weights can be adjusted by you based on the relative importance of each aspect for a given task. By incorporating syntax and semantics, CodeBleu provides a more comprehensive evaluation of code correctness compared to purely text-based metrics. The multifaceted score captures different levels of similarity between the generated and the reference code. One key advantage of CodeBleu is its flexibility. The weights of the components can be tuned for different programming languages or different programming tasks. This adaptability makes it a versatile metric for various code synthesis applications. So, to recap, CodeBleu evaluates code synthesis results by comparing 4 main aspects: the standard Blur score, weighted n-grams, syntax via ASTs, and semantics via data flow. This holistic approach aims to provide a more reliable and informative score compared to existing metrics. When evaluating code similarity, it's crucial to look beyond the surface level differences and focus on the underlying structure and functionality of the code. This is where abstract syntax tree matching comes into play. ASTs represent the hierarchical structure of the code, capturing the essential programming constructs while abstracting details away, like the variable names and formatting. In this illustration, we'll explore how AST matching can reveal the equivalence between 2 code snippets, even when they use different syntactic constructs. On the left side of the screen, we have the reference code, which defines a function called max. This function takes 2 parameters, a and b, and returns the maximum value between them using a traditional if-else statement. On the right side, we have the candidate code, which defines a function with a different name, in this case, findMax. This function also takes two parameters, in this case again named differently, x and y, but it uses a concise ternary operator to determine and return the maximum value. The ternary operator is a shorthand way of writing an if-else statement in a single line. It evaluates a condition and returns one value if the condition is true and another value if the condition is false. Now let's observe what happens when we transform the code snippets into their corresponding abstract syntax trees. Each node in the tree represents a specific programming construct, such as function definitions, conditional statements, and return statements. As we compare the ASTs side by side, we can see that despite the difference in using an if-else statement versus a ternary operator, the overall structure and logic of the two trees remain the same. Both ASTs have a root node representing the function definition, with child nodes representing the conditional logic and the return statements. The specific condition and the values being returned may differ in their representations, but the fundamental functionality is equivalent. Based on this structural and functional similarity, the AST matching algorithm assigns a high score to the candidate code. It recognizes that the generated code achieves the same result as the reference code, regardless of the specific syntactic choice between an if-else statement and a ternary operator. This high AST matching score indicates that the candidate code is a close match to the reference code in terms of its underlying logic and behavior. So AST matching is a powerful technique in code evaluation because it focuses on the essential structure and semantics of the code rather than getting distracted by syntactic variations. Now let's take another example to look at data flow matching. In this scene, we have the reference code on the left and the first candidate code on the upper right. Let's take a closer look at these code snippets. The reference code defines a function called greater than that takes two parameters, a and b, and returns a Boolean value, indicating whether a is greater than b. It uses a simple if-else statement to compare the values and return the appropriate Boolean. Candidate code 1, on the other hand, defines a function called first is larger that takes two parameters, x and y. It uses a ternary operator again to return 1 if x is greater than y and 0 otherwise. Now, let's introduce a second candidate code snippet, candidate code 2. This code snippet is identical to the reference code, except for one crucial difference. In the if-else statement, the Boolean values returned are swapped. If a is greater than b, it returns false, and otherwise it returns true. This is wrong. So when evaluating these code snippets using the blur score, candidate 2 would likely receive a high score compared to candidate 1. This is because blur focuses on the surface level similarity of the tokens, and candidate code 2 shares more identical tokens with the reference code. However, CodeBleu takes a more comprehensive approach. It considers not only the token similarity, but also the structure and meaning of the code. When we examine the semantic meaning, candidate code 1 stands out, although it uses a different approach with the ternary operator and returns integers instead of Booleans. The semantic meaning is consistent with the reference code. It correctly returns a value indicating whether the first parameter is greater than the second. But on the other hand, candidate code 2, despite its high token similarity, has a crucial semantic flaw. By swapping the Boolean values returned in the if-else statement, it completely changes the meaning of the function. It now returns the opposite of what the function name greater than suggests. When calculating the CodeBleu score, the semantic mismatch in candidate code 2 would be penalized by the data flow match component. As a result, candidate code 1 would receive a higher overall CodeBleu score, reflecting its semantic correctness, even though it has a lower token similarity compared to candidate code 2. This example highlights the importance of considering both syntactic structure and semantic meaning when evaluating code snippets. While Blur relies heavily on token similarity, CodeBleu provides a more nuanced assessment by incorporating AST matching and data flow analysis. It recognizes that preserving the semantic integrity of the code is crucial, even if the surface level similarity is lower. By taking a holistic approach, CodeBleu helps identify code candidates that are not only syntactically similar, but also semantically equivalent to the reference code. And this is essential for ensuring the correctness and reliability of code synthesis and evaluation tasks. So let's put all of this together and look at an application to compare different LLMs using CodeBleu. This gives us the opportunity to come up with our own test cases that are truly representative of what we want our coding LLM to do. We might have designed it to write whole classes, or it may be we're focusing it more on fine-grained analysis and look at specific functions implemented in classes. Alternatively, we might design our coding LLM to execute API calls in a library. By designing our own tests, we can supplement rankings in league tables like HuggingFace with more specific tests that are truly representative of the code that we want our model to generate. Not only does this allow us to compare third-party models more precisely, but if we're fine-tuning our own models using our own fine-tuned corpora, it gives us an objective way to compare our own model implementations. So for this specific test, we're looking at implementing a Flask application in Python to interact with a database and provide simple create, read, update, and destroy functionality. You can see this specified in our test prompt. We need a corresponding golden source code template for this test. This is the reference code that we will compare the candidate code to and provide a CodeBleu score to reflect the similarity. So we can drag both the prompt and the golden source into our application. For this example, we'll test both with some hosted models as well as some models that I'm running locally using Ollama. In this case, the hosted models are the out-of-the-box foundation models from OpenAI and Anthropic. Neither GPT-4 nor Claude 3 have been fine-tuned for code generation. But as we mentioned earlier, they've both been exposed to sites like Stack Overflow, so have a pretty good coding foundation. We'll also use CodeLlama, WizardCoder, StarCoder, and CodeStable, which are all specialist fine-tuned coding models. They're all available from Ollama, and for this demonstration, they're all running locally on my machine, which is a Mac Studio built on an M2 chip with 128 gigabytes of unified RAM across the neural engine, GPU, and CPU. Now, I'll be straight with you, I don't know precisely what all of that means, but I do know that it's a powerful enough computer to run these models locally. We can first check that the golden source has been loaded up. While the formatting is off, you can see that the code is preserved in this drop-down inspector. We can then see the code produced by our first model, GPT-4. As ever, do feel free to pause and rewind the video if you want to look more closely at the code being generated by the models. You can see here that GPT-4 understands how to format and color Python code natively. Next up is Claude 3 from Anthropic. Again, please pause and rewind to inspect the code at your leisure, should you wish to. After this, we have CodeLlama, shortly followed by WizardCoder. The last two models you'll see have completed and the results printed out before I shut down the WizardCoder candidate. As the stable coder version seems to have topped this particular benchmark, I'll run the inspect code so you can check it out if you want to, again, by pausing and rewinding. Below all the candidate code examples, I display the CodeBleu results from 3 different visualizations. Firstly, as a grouped bar chart, then as a table, and finally as a radar plot. This shows the overall CodeBleu score, as well as the individual components of the score that we discussed earlier in this video. The winner in this case is StableCode, a model provided within the Ollama framework and hosted locally. Now, does this mean that this is the best available coding LLM? Not at all. It does mean that it scored the highest on this test with this set of model hyperparameters, but it clearly does not follow that it would beat the other models when prompted to perform other coding tasks. And that brings us really to the main point of this video. If you're evaluating different models for code generation, or if you're building your own fine-tuned models, then building your own test applications is a really important step. We're all building these LLM apps with a massive piece of non-deterministic functionality right in the heart of things, the LLM itself. These aren't like other apps we've developed before. By all means, pay attention to benchmarks on Hugging Face, but to truly evaluate how good these models are for your task, please consider supplementing the Hugging Face benchmarks with your own tests. If you're using an LLM to write classes or specific functions or make API calls, then your tests should reflect that. Likewise, if you're writing in Java, Rust, Julia, Python, Go, etc., then perform specific tests to test the models on those languages too. Lucidate members at the managing director or CEO levels will get access to the source code for this testing application and an instructional video on how it's built and how it works. You'll be able to use this application as is or enhance it to add your own functionality. So to sum up, when evaluating code generation models, it's crucial to consider both established benchmarks and custom tests tailored to your specific use cases. CodeBleu offers a more comprehensive evaluation metric by considering syntax and semantics alongside token similarity. By creating your own tests, you can ensure that the models you choose excel at the specific coding tasks relevant to your projects. Happy coding and evaluating. I hope this video has provided you with valuable insights into evaluating code generation models and the power of CodeBleu. I encourage you to explore the resources mentioned in the description and learn more about this fascinating topic. If you found this video helpful, please like, share, and subscribe to support the channel. Until next time, keep exploring the exciting world of AI and code generation. This is Richard Walker from Lucidate signing off. I'd love to hear your thoughts and experiences. Have you used CodeBleu or created custom benchmarks for your projects? Share insights in the comments below and let's continue the discussion. If you have any questions or suggestions for future topics, please feel free to reach out. Stay curious and keep pushing the boundaries of what's possible with AI and code generation.